Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing our examination of the derivatives of carboxylic acids. Specifically, we're going to begin looking at anhydrides and anhydride chemistry. Now, anhydrides are molecules that result from the dehydration or loss of water from two carboxylic acid functional groups. Here we see two ethanoic acids, or common name acetic acids. If one ethanoic acid loses an OH and the other loses an H+, the OH and H+ can combine to be a water, and the remaining molecule can attach to form what is referred to as an anhydride, an anhydrous version, if you like, of a carboxylic acid. It has lost water. This anhydride that forms is symmetrical, and I've recorded the name here. Let's examine the nomenclature of such anhydride molecules. The rule for naming anhydrides is pretty simple. Essentially what it involves is dropping the word acid and replacing it with the word anhydride. Hence, ethanoic acid becomes ethanoic anhydride. Acetic acid becomes acetic anhydride. Note, if there's only one designation in front of the word anhydride, it means that the anhydride is symmetrical. If, however, an anhydride formed from two different carboxylic acids, it would not be symmetrical. On this side, or the left-hand side of the anhydride, we see a 4-carbon chain, which means that it was made from a butanoic acid. On the right-hand side, we see a 3-carbon chain, which means it's from a propanoic acid. In this case, you name both acids, butanoic space propanoic anhydride. And in IUPAC nomenclature, you attempt to remain alphabetical in your arrangement of the names. Now, cyclic anhydrides we've already examined. Cyclic anhydrides can be derived or named after their parent carboxylic acid. This anhydride right here formed from a dicarboxylic acid. There are 4 carbons in that ring. This is a 4-carbon alkane. The IUPAC name for this molecule is butane dioic. Hence, this molecule would be butane dioic anhydride. The common name for the dicarboxylic acid is succinic. So succinic acid becomes succinic anhydride. So long as you know the parent carboxylic acid, long as you can determine the name for the parent carboxylic acid, it is fairly easy to name the anhydride. Okay, how are anhydrides prepared? Well, obviously, if we look at the top reaction, any methodology that can remove water can be used to produce an anhydride. However, the loss of water does not have to take place from the carboxylic acid directly. In other words, we don't have to go directly to an anhydride. Anhydrides can be prepared from other functional groups. For example, in order to prepare an anhydride, we could take a carboxylic acid, and as in the last Scribblecast lecture, we could convert it to an acid chloride using thionyl chloride, SOCl2. SOCl2, remember, replaces the OH group with a chloro group. We then could take some other carboxylic acid, such as benzoic acid, and treat it with base, such as sodium hydroxide. Base deprotonates carboxylic acids and it would make benzoate anion. If we react the acid chloride with benzoate anion, a benzoate anion is a weak nucleophile, but acid chloride is so reactive it will react with it, giving off the good leaving group Cl-. Remember, the process involves benzoate attacking the carbonyl. You actually will form an intermediate, looks like this, and then the alkoxide oxygen will dump in its lone pair of oxygen, create the pi bond, kicking out the chloride. So the intermediate will convert, once chloride is lost, to CH3, C double bond O, O, C double bond O, and we will make benzoic ethanoic anhydride, or benzoic acetic anhydride. Or you could equally say, in common nomenclature, alphabetizing is not crucial, you could say acetic benzoic anhydride as well. Try to alphabetize when you're using AluPac nomenclature. Alright, now, what's nice about this procedure is the yields are high, as well as it's a nice route for making asymmetric anhydrides. We could have used the same carboxylic acid, but you equally can use different carboxylic acids and get high yields of asymmetric product. A less efficient way, but it works as well, is if you use another anhydride to dehydrate a carboxylic acid. For example, we might take a molecule like benzoic acid and stir it up in the presence of acetic anhydride. So we might take some ethanoic anhydride, stir these two together, and what happens is the anhydride can actually scavenge the proton off the carboxylic acid. Okay, it can get attacked by the carboxylate here and kick out CH3CO2-. And effectively, you can convert and produce acetic benzoic anhydride or benzoic ethanoic anhydride, the asymmetric one. Of course, formed in this reaction is a molecule of ethanoic acid. Now, the acetic benzoic anhydride can further react with more benzoic acid to go all the way and convert to benzoic anhydride. And you get given off a second ethanoic acid. All right. Now, what's nice about this is that you're using one carboxylic acid to convert another, but the problem is it's an equilibrium, and so the yields distribute between the three possible anhydrides. In order to drive the reaction all the way to benzoic anhydride, you must raise the temperature of the reaction to the point that you distill off or remove the ethanoic acid. If that is removed, the equilibrium will shift to the right, and you'll get more appreciable yields of the desired product, benzoic anhydride. Also, you should remember that heat can be used on cyclic dicarboxylic acids. Sorry, not cyclic dicarboxylic acids. I mean just dicarboxylic acids to form cyclics. So if I take something like glutaric acid and I apply heat, I can make glutaric anhydride. Now, we've already covered this in a previous Scribblecast lecture, but it is preparation of cyclic anhydrides. So there you have it. You can prepare acid chlorides, attack them with carboxylate to make anhydride. You can use anhydrides to dehydrate other acids and make new anhydrides, or you can take dicarboxylic acids. As long as they form an optimum ring structure that's not strained, they will form anhydrides. Okay, let's examine the reactivity of anhydrides. Take a close look at the reactions. Acid anhydrides undergo the same reactions with the same nucleophiles as acid chlorides did. In fact, I could almost say, refer to the acid chloride Scribblecast. The only difference, however, is that the rates of reaction are slower because the carboxylate leaving group is a poorer leaving group. It's not as good a base, not as weak a base as Cl-. The carboxylate anion doesn't leave as readily as the chloride ion. The process is nucleophilic acyl substitution, just as the case for acid chloride. So what you're going to see is exactly the same. Nucleophilic acyl substitution. You almost need to call this the standard mechanism for reactions of carboxylic acid derivatives. Now, nucleophilic acyl substitution is a two-step process. We did it for acid chlorides last time. Let's look at it for anhydrides. Step one, of course, was nucleophilic attack. So, if we have some anhydride, remember last time right here would have been a chloride, but instead we have the anhydride. So there's a carboxylate attached to the acyl group. We attack this with our nucleophile, called Nu. Has a lone pair Nucleophile goes for a carbonyl. This pushes electrons out on the oxygen. We get R, C, O minus, O, C double bond O, R, and a nucleophile attached to it. Now you might be thinking that another nucleophile can simultaneously attack the other carbonyl. This is much reduced in probability because of the buildup of negative charge on the molecule. The presence of the negative charge on the oxygen will increase the repulsive forces against the nucleophile. Getting two nucleophiles attacking an anhydride is a very low probability event. So, step 2 happens before anything like that can happen. And that is elimination of carboxylate. In the acid halide case, it was elimination of chloride. Carboxylate is a stronger base than chloride, and as a result is a poor leaving group. So the reaction is slightly slower. But this step in both mechanisms, loss of chloride or loss of carboxylate, is the fast step. The slow step is nucleophilic attack. So we got R, we have the O minus, we have our anhydride carboxylate that's going to be kicked out. We have our nucleophile. The pi electrons from the oxygen come back in to form the pi bond. The carbon-oxygen bond breaks. Electrons go to the oxygen. You end up with R, C double bond O nucleophile. And you get carboxylate. So you're going to notice in every one of the reactions we look at that this indeed is the mechanism that takes place. Okay. So there you have it. Let's start looking at some specific reactions. The first one is hydrolysis, or reaction with water. Remember, reaction with water is what makes a molecule carboxylic acid derivative. You are carboxylic acid derivative if when you react with water, you form carboxylic acid. If we take our anhydride, and we just use a generic functional group, R represents some alkyl, or it could even represent hydrogen. We take this anhydride, react it with water. The water molecule attacks as our nucleophile. We get R, C, O minus, O, H, H plus, O, C double bond O, CH3. What happens now? Kick out the carboxylate. Very quickly we get R, C double bond O, O, H, H positive. And the leaving group, of course, is the carboxylate. And very quickly, the proton can transfer, and you end up with two R, C double bond O, OHs. Oops. Oh, my CH3 appeared out of nowhere. That should have been an R group. Could be a CH3. There we go. Now we just use water here because if we actually use the base to help remove this proton, then we'd end up deprotonating the final acid. So we typically don't use a base here. What's interesting though is reaction with water is similar to reaction with alcohol. I could replace one of the H's on water with a carbon. Instead of water, I could use methanol. If I did that, I'd call this reaction alcoholysis. Or cleavage with alcohol instead of water. If I did that, where water attacked, I would have it replaced with the methanol. I'd have a CH3OH plus, and this would be a CH3. Now, because we're forming ester here, I'm not worried about deprotonating. We often throw in a base to help drive this reaction. And the base we throw in is pyridine. Pyridine is a poor nucleophile because its lone pair of electrons on nitrogen are in sp² orbital, but sufficiently basic to remove the proton. Okay, remove the proton from the protonated ester. It will leave as a pyridinium cation. Okay, and so we will finish with R, C double bond O, O, okay, and the ester. Put the CH3. And then we will have also pyridinium, a salt of pyridinium carboxylate. So if it was methyls, if the R group were methyls, it would be pyridinium ethanoate or acetate. Now this addition of the base, this salt, is easily extracted into water and allowing you can distill off the ester, recrystallize the ester, separate the ester, extract it into an organic layer. It's fairly easy to purify. You don't do this pyridine when you use water. Remember water, what did water generate? Water generated the carboxylic acid. If you use pyridine, you would deprotonate your acid. And you don't want that. You want to make the acid. So when you use water, you can't use pyridine. But you can use the pyridine to facilitate the proton loss and drive the reaction completely to ester. So reaction with water makes carboxylic acids. Okay. So if we use water, we get carboxylic acid. If we use alcohol, we get ester. Okay. Let's take a look at reaction now with amines and ammonia. So let's react either with NH3 Or we could use a primary amine, or even a secondary amine. Primary or secondary amines. Okay. What happens if I take CH3, C double bond O, O, C double bond O, CH3. And let's use methylamine just like we did with acid anhydrides. With acid chlorides. In the previous scribblecast, we used methylamine. Well, the exact same mechanism happens. The only difference is the leaving group changes. And so the carboxylate bond reforms, kicks out, or the C double bond O reforms, kicks out carboxylate. We lose minus the carboxylate anion at the NO8. And we end up with a protonated amide. Now, because amine's relatively cheap and a powerful base, you can use two amines in this reaction. The second amine comes in. If you use two equivalents of methylamine, it grabs a proton, goes off as methylammonium cation. Okay. If it deprotonates, we end up finishing with an amide. In this case, it's based on ethanoic acid. You haven't learned the nomenclature of amides yet, but this would be an ethanamide with a methyl off the nitrogen, so N-methylsuccinimide. Or, because it's based on acetic acid, acetamide and methylacetamide. So effectively, we are able to get to this by addition of two equivalents of amine. Now, there is a special case of the cyclic anhydride. What happens if you treat a cyclic anhydride with ammonia or amine? Well, let's try the same reaction, but this time let's attack succinic anhydride. Now, just because it's cyclic doesn't mean it's not going to react. In fact, it reacts the same way, except one end of the chain will be your leaving group, one end of your ring. If we use methylamine and it attacks, we get the exact same first step. We have an O minus, and we have an NHH CH3 plus attached there. Now what happens here is the pi bond reforms and the CO2 minus on the other end leaves, and we very quickly go to a CO2 minus. We have a double bond O. And we have this N and H2. Still too many H's here because it's positively charged. And so methylamine can come in. If we use two equivalents, just like before, can come in and deprotonate, so it becomes methylammonium. Cation. It grabs the proton, and we have the carboxylate salt. Now we covered amide bonds in amino acids. And one of the things we learned about in amino acids is that the amide lone pair is not basic. One could argue and say that would not the carboxylate, because it's intramolecular, grab the proton and you get the amide and the carboxylate? Certainly there would have been an equilibrium from this structure if you used only one equivalent of methylamine. The CO2 minus may have grabbed the proton, in which case you would have gotten this. If you had actually isolated the carboxylate, this derivative, you could get to this species by addition of H+. So if you had gone plus H+, you could have made it. So we can get a carboxylic acid on one end and an amide on the other. Now the amide, because it's resonance stabilized in C double bond O, is not very basic. It's also not very nucleophilic. But because it's an intramolecular rearrangement, it certainly is possible to put enough heat in the system so that the lone pair that is here can actually collide with the carbon of the other carbonyl, and you'll get to this guy. As soon as that forms, you've got this extra H plus on the nitrogen. And so let's draw that H plus, if you don't mind. And you see you're all set to reform a pi bond here, kick out OH minus, and have the OH minus grab the proton. And get the lone pair forming on nitrogen. If that happens, you lose H2O, and you get OH is gone, and H off the nitrogen is gone, and you're left with this. Well, it looks like almost like an amide. You have a C double bond O with an N, but you have two C double bond O's. And this is called an imide. It's based on succinic acid. This was succinic anhydride. And so this would be based on succinic anhydride. It becomes succinimide. But there's a methyl off nitrogen, so we call it N-methylsuccinimide. Now you can stop at the carboxylate. You can stop here. If you use two equivalents, you can deprotonate, and this will not occur as long as this is carboxylate. But if you go to the carboxylic acid amide derivative, then you can apply heat and take it right through to N-methylsuccinimide. That is, convert the anhydride into the imide. Okay, well that's it for the reactivity of anhydrides. It's a rather short section. As you've seen, the chemistry is very similar to what we've learned in acid chlorides. There is only this little extra portion for cyclic anhydrides. Next Scribblecast lecture, we're going to begin looking at esters. Now, esters as a functional group are a very large grouping. That is, there's a lot of chemistry, and esters are very important. So we'll be spending probably several Scribblecasts looking at the chemistry of esters. We're progressing slowly through all the carboxylic acid derivatives. Acid chlorides and anhydrides we've just covered. Esters, amides, and nitriles remain to be covered. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.